So just from my side, I just want to say that I'm very, very glad to be here. And today I will be talking about machine learning, which will be an introductory, actually, lecture. I know some of you probably have a very good understanding of all these things that I will be talking about, but I also know that some of you are not. So I hope that I will give like a kind of a high level presentation of machine learning, some of the main kind of aspects and algorithmic kind of insights that also could be probably used by people who are not kind of experts in the field, but it would be nice for you to understand how all these things are built and trained, and this will probably help you if you're interested in going further into artificial intelligence. Yes. I can share the slides, definitely. Yeah, you don't need to take notes. It's okay. All this information that I will present, they are broadly available. I will just gather them and organize them in a kind of clear way. By the way, I'm just adding here that at the end of this hopefully quick presentation, there will be a hands-on workshop where you'll have to actually write a bit of code yourselves. If you have your laptops with you, it would be nice to actually see how are these things programmed, and you will also be able to solve a very simple, not so simple, but a very simplified problem. Okay, so just a little bit of background for us. I'm Sterios, and Maria will be joining us soon. We are both assistant professors at the University Paris-Saclay, specifically on the Central Supélec part of it, and we are and we have a background, both of us, in engineering somehow. But eventually, at some point, we moved towards artificial intelligence applied to healthcare and medicine. And right now, we are in the same lab, and we are working towards cancer care and solving issues related to health, let's say. Maybe the other way. Okay. So another thing before starting is that tomorrow we'll also have a similar kind of lecture, but this will be mostly focused on deep learning, which is like somehow the latest advances in AI. But I will start from the basics, okay? So just a quick motivational slides in order to explain to you why we're interested in using machine learning in healthcare. And the main idea, in contrast to what it was believed at the beginning, is that actually we want to have some kind of collaboration between clinicians and engineers or AI experts, let's say, in order somehow to design, develop, and assist in different aspects of healthcare and the clinics, like drug discovery, biomarker identification and discovery, patient stratification, and other kind of really important aspects of the everyday life in clinic. And due to the latest advances in AI and artificial intelligence and all this kind of what was also discussed earlier, we got like somehow the ability to parse large amounts of data and get some kind of notion out of them. And the idea is to have like systems that are collaborating, like collaborating with clinicians and other persons that are somehow experts in the field. Here is just like a broad picture of coming from a review paper where I'm just showing the vast majority of applications that you can have. Here are only a few, especially in drug discovery. And these are connected to different kinds of methods that I will briefly talk about in a while, which is like supervised learning and clustering methods and other things. And just a slide that you probably know about is the AlphaFold advance that it was made only recently, where researchers managed to get some kind of a data-driven system to automatically predict the structure and the 3D shape of proteins which otherwise was only feasible through very expensive and laborious processes. And at the moment, most of the known proteins are publicly available. Their 3D shape and structure is publicly available, which is believed to help a lot in moving forward drug discovery and understanding of diseases. Okay, I will just start by giving you like a broad picture of what the machine learning pipeline is. And then I will briefly talk about the different aspects that you might hear when you're listening and hearing about machine learning. Okay, so there are some tasks that actually are uh, for which we don't actually need learning or some kind of machine learning approaches. Okay, so for example, if someone needs to calculate their taxes, you don't need to have a system trained for this purpose. You can follow a bunch of rules, and then you can somehow generate answers. Okay, but and for this you can have like classical programs to do so. Okay, but when we're talking about machine learning, the main difference is that in fact you don't have human expertise because it is either not existent or it's not known or it is very difficult to calculate. Like you have some very complex situations and environments that are kind of difficult to model, and that's why you don't actually have all this knowledge to go through the kind of typical pipeline. And for that reason, you can actually use machine learning algorithms where, in fact, by combining at the same time data and answers, which means what I have and what I want, eventually our model, our program to do, we can generate what I write here rules, but in fact is some kind of an algorithm that when it is fed with data, it provides answers. Okay, this is kind of the general idea. And in this case, is actually we need to go through this kind of learning process. We need to somehow utilize a machine learning tool. And throughout the presentation, I will be using this running example of separating pictures to either belong to a class which is a dog or a cat. Okay. And the idea is that how can we have a computer and how we can train a system, how we can devise a program to automatically perform this task for us. Because it is not quite straightforward how to do this, okay? So you might think quickly that, okay, if I find like pointy ears in the image, then it probably means that it's a cat. But then we are talking about images, and then you'll have to have very broad programs that work for any position and any angle of the ear, let's say, okay? So the general idea is that it is quite simple, and it is based on the fact that when you have a lot of examples and you feed your system with all these examples, somehow you can extract relevant information and learn ways to discriminate between, for example, these tasks, okay? And you can think, while talking about this, or you can think about different tasks, like deciding whether a patient will survive after this amount of time or not, okay? I hope it will get more and more clear as I'm going through the slides. So the idea is that the way we are doing this is that we are going from this to something like this. We are using information that is broadly available, and it comes in quantities from the internet, for example, in these types of cases, where we're using a lot of data to somehow identify information from this data and use all this information to make our prediction. And I will show you how. So coming back to a bit more pragmatic version of what is a machine learning system is that we have a bunch of data. We also have what it is called a training process, which means how our model or how our system is learning all this information. And then when we have some kind of unseen data, some data that is not available during all this process of training, then the model will be able to make a prediction, okay? And so in essence, we have this kind of block, which is the input data. Then we go through some process of identifying information in this data that are somehow discriminative, and I will give you a bit more details about this. Then we have the training process. Then we have this, what is called the model. And then we have what is called the test data, which when applied, when the model is applied on this data, you get some output, okay? So this is a typical machine learning scheme and the pipeline. So for this, you need to know about your input data. You need to know how to represent your input data when your input data is images, or when your input data is voice or clinical data or whatnot. You need to know how to represent this data. You need to define a specific model to work on this data. You need to define a training process, and then you need also a different pipeline to make sure that your model is actually doing what you want to do, okay? So let's start from this. And what I mean about this is that in this example, as I was also explaining before, since these are images, and images lie on some kind of data structure that is in fact numbers in the memory, you don't necessarily know where to look in this. There is a large array, a large matrix, let's say, with all these numbers that represent the different colors and the intensity of the different colors. And you need to go through this image and this data structure and identify different characteristics, okay? So our goal is to somehow extract all these characteristics, all this information from all these images and make it such that computers and programs are able to work with this, okay? And in fact, in this exactly point here, the deep learning came to give a very solid impact, and we'll talk about this also tomorrow. But initially, the idea is that you need to identify characteristics in these images that somehow are descriptive of what you want to do. So in this example, it might be some kind of an estimate of the size of the animal and some kind of an estimate of how pointy their ears are, okay? And based on this, you can identify somehow how to discriminate them. And of course, this is subject to kind of the performance. Let's say if you find other discriminative features better than this, maybe your model or your algorithm will work better eventually, okay? So this is the first step of feature extraction. And then I will move to the model. So what is the model? So at first we have like our data. We defined, let's say at the moment, some process to extract useful information from our data. And now we want to see what these models are, these fancy neural networks or whatnot, okay? So there are many different models that you can use. Some of them are very simple, which are linear, which means you eventually learn a specific line that discriminates between these. So because here, for example, eventually each of the images, it's represented by two numbers, which is the size and the ears, how pointy they are. So there are little dots in like a space like this. So you can actually define a line that separates these, okay? And these lines are linear models, which I will be talking in a bit more details in a while. Then you can have different other borders that are more kind of precise, or they are non-linear, where you have like curves or whatnot. Or you can have different models, which typically called generative. I'm not going to go into details, but in essence, here you just learn what is the distribution of the characteristics of a single class, and then you use this to make your decisions, okay? Vaguely speaking, all right? I'm just going very high level here, because also 1 hour for an introduction to machine learning is quite short. Okay. So eventually what you'll have to do, since you have a number of data, you have a way to represent them in like a compressed way, let's say. Then you have to identify which model it's appropriate for your use case. And then after selecting the model, you can move on to the training process. And the training process is what eventually makes the model do what you want, in fact. And the way you do this is that all these models are in some way parametric, okay? So there is some kind of parameters that actually define exactly the characteristics of the model. So if we are talking about a line, the line can be described by what is the direction and the distance from the zero, let's say. And so, in fact, by showing it examples in an iterative manner, you just learn how to do this fitting, how to change these parameters of your model, in this specific case, the linear model, in order to have some sort of a separation, okay? And then when you have this line, it's quite simple. If someone comes and gives you a new image, you will know what to do, right? You will calculate the pointness. I don't know if this is a legit word, but how pointy the areas are and the size. You'll have a dot in this picture, this plane, and then you will say if it is below this, it's a dog. If it is above this, it's a cat. Okay? In a very simplistic terms, this is the overall pipeline. And of course, for all these different components, there is a lot of research throughout the last decades, even more, on how you can actually represent data, in what form you represent different types of data. If you're talking about medical images, if you're talking about sound, if you're talking about whatnot, text. Then there are different models, which I will give you briefly some names to keep in mind if you see them in front of you. And in terms of training, you have different optimization processes on how you can actually change the parameters of the model to fit your data, okay? And then there is a very crucial part, which is the how you can evaluate that your model is doing well. Because as you can probably guess, your model knows as much as your data. If you have a model that it is trained on separating dogs versus cats, then if you provide a tiger, the model will give an answer, definitely, but the answer will be, you know, it can be whatever. So an important aspect of machine learning and AI research is how you can actually evaluate your models and make sure that your model is performing the way they are supposed to. And specifically in healthcare, that whatever the output is here, it is very, very important and crucial for patients' health, okay? All right. So after all this first part of this introduction, I will just go into giving you some more details on different kinds of machine learning models and schemes and applications that you can find. I don't know if you have any questions before going there. Yes? Not necessarily. What I will come to this again later in the presentation, but the general kind of idea is that you want to have your input data as to have the more variability possible, but you also need your test data to have this. So you cannot train a model in detecting different types of cancers and then check only on a specific cancer case. So you need to define your evaluation criteria of your model to follow somehow the principles that make sure that your model is performing what you want. So there are not clear guidelines on what to do. You just have to do the best. And typically in healthcare, because getting data, some of you are lawyers, I guess, so you know about GDPR. it is not so straightforward to get data. So it's quite complicated. We need to work in collaboration with hospitals, etc. So yeah, I'm stopping this rant now. Okay, so going to a more kind of grand view of different machine learning applications and methods. You can find these different kind of categories of machine learning models. I will start from here, which is typically called the supervised learning, where it's more or less what I was discussing. So you have a set of data, and you also have a set of answers, meaning pairs of input and outputs, what you want to provide as an input and what you expect as an output. And these are called supervised learning methods. And within the supervised learning methods, you have methods for classification, methods for regression. This means that for classification, we want to make a decision among a set of different answers, while for regression, we want to make a continuous prediction, like predicting the temperature, for example, okay? And then in the part of unsupervised learning, you have clustering, which means organizing and grouping together data points that have similar structure and similar characteristics. And dimensionality reduction means ways to make our representation of the data smaller. Okay. I'll come in a bit more details in a bit more visual way again to this. And then lastly, we have reinforcement learning, which is in fact the science of learning how to learn through interaction. Okay, so you can think of machine learning models that are thrown into some kind of environment. A very simple use case is like a robot walking around in a room like this. So you throw this robot in, and then you want to have methods for this robot to learn how to interact with this environment and learn some specific task. Okay, this is clearly different than unsupervised learning, but also it is clearly different than supervised learning because in fact you don't have some kind of supervision. You cannot say to the robot, you want to do this, or you have to do this. The model needs to learn by itself. I'm not going to talk about this much in this presentation. I will mostly focus in the other parts. Okay, so starting from the unsupervised learning scheme, we have this kind of data, which is a data set of multiple points, multiple examples, which are represented here. And then the unsupervised learning paradigm is mapping these types of data to some other kind of data, which have different characteristics. Okay, so this means that we are learning from our data different representations of the same data. Okay, this is what we mean when we're talking about unsupervised learning, and there are a lot of research in this kind of domain, because in fact in the internet you can find really a lot of data, but not all of them have quality annotations or quality annotations. So there is a lot of research in learning ways and identifying ways to learn new representation of the data that are useful for a specific task. I think Maria is looking for her way to enter. Okay, so a special case of unsupervised learning is the case of dimensionality reduction, where in fact the task here is not only to learn a new representation of your data, but also learn a smaller representation of your data. Meaning that you want, so here is a table to represent your data. For example, you have different rows in this table, which are all the different examples, and you have this P here, means all the different features, all the different characteristics you learn from the data. And you want to learn a mapping such that this is much smaller, okay, and more useful. So for example, when you're talking about images of very large sizes, you want to transform an image of the dimension 256 times 256 pixels times 3 color channels to like 5 values, okay? And there are machine learning algorithms that do this automatically. And you can actually see this a lot in the recently literature about deep learning methods. All right. And yeah, I just answered this, so why dimensionality reduction is useful. You can actually reduce the size of your data by, this will help in storage as well as computational time. It sometimes can remove redundancies because an image like that, for example, has a lot of information which is actually redundant. You have thousands of pixels which are blue, which describe, for example, the sky, but you probably just need one to tell you that there is a sky, for example, okay? And of course, you can use these types of methods in order to visualize. So if you have like data sets that lie in very high dimensional spaces, you can downscale all these spaces to 2 dimensions and plot them in 2 dimensions, for example, and see them in front of you on how they organize themselves. And okay, and then we have clustering, which is the process of identifying similar points, okay, similar data points from your data, okay, and this is specifically useful for identifying different customer groups, identifying different subtypes of diseases, etc. Okay, and then comes the supervised part. I finished with all the unsupervised components, and now I'm moving to the supervised learning paradigms where you actually learn and train systems in order to make predictions now, okay? So you have input data of any size and any dimensionality, and then you have also labels now, you have annotations, you have information of what is their true identity, let's say, okay? In the case of the cats and dogs, you have in here in the rows the different pictures. This dimension will show you pointy ears or size, and here you'll have labels will tell you that this is a cat or this is a dog, this is a cat and this is a dog, okay? And the task now for the machine learning algorithm is to actually learn this decision function, learn this mapping that takes X, the input, and transforms it into the Y, okay? And as I told you, we have, yes, we can have cases where we want to make discrete prediction, meaning different classes, cat versus dog, or different subtypes of diseases, malignant or benign or subtype A, B, C, or etc. But you can also, yeah, I'll come to the also part in a while. Okay. So again, here now, given a specific data set like this, now you have pairs of representative features of your data points and different output or targets, which are typically looking like this. So you have 1 to define that this is a dog, and -1 that this is a cat, okay? And then your task is to identify this separation between the two. And these are a number of applications that you can, of course, see, like face recognition, where you now have to identify faces independently of their pose, or different kind of applications, like, for example, in the self-driving cars that I'm having here a how question. Do you have any idea of how supervised learning can be used in such a scenario? There are in fact many different problems to solve when you want to learn how to drive a car. Yes, go ahead. Yes. There are actually a million of choices that you have to take when you're learning how to automatically drive a car, like to identify where there is a street, where there is what are the signs, what are the colors of the lights, where are the humans, how should I steer the driving, how should I steer? It's fine, right? uh, yeah. Okay. Um, yeah. Okay, and then from the other side, we have supervised paradigms, but now instead of predicting different categorical, as they're called, outputs, we are predicting something continuous. We predict a value that can range from 0 to any arbitrary number. Okay, and what we have to do is to identify ways to approach all these problems. And all these are different applications. And as an example here, I'm plotting the case where you want to predict the train occupancy by using only as a feature the time of the day. And you have different kinds of data points, and you want to fit a curve here. Okay? Yeah, and here, again, some examples. Any questions? Between unsupervised, supervised, clustering, regression. You understand all these topics now, I hope. I mean, as like their names. I mean, you can say yes, I've heard this before. It's something about predicting continuous values. Okay, so the general kind of idea and setting is that you always need the data. Okay, we're talking about data-driven systems, and you always need data. Whether you have paired data or unpaired data, meaning when you have pairs of input and output data or not, there could be some kind of system to be utilized in order to extract information, like identify specific structures within this matrix, or finding ways to make the mapping between going from the input space to the output space. Okay, and as I discussed before, this output space can be binary classification, which means positive versus negative, multi-class classification, which means bird, human, airplane, car, multi-class classification, and also regression, which is the continuous value. So quickly, I will talk about linear regression, which is the most basic machine learning model that you can have. And the idea here, and now I'm going into a bit more details on what I mean by saying that we have parametric models. The idea here is that given a specific input, x, we would like to take this input and transform it to some output. Okay, this is the general idea: getting the input and making a prediction. And the idea with linear regression is that we want to learn these parameters, theta 0 and theta 1, which make this mapping possible. And these linear models, for example, I'm just showing here the case where we have the x dimension to have only a single value, which means that the points will lie somewhere on this space, okay? And we want to transform this axis into this, okay? So this is a very, very simple equation. And by properly setting this theta 0 and theta 1, we in fact change the angle, the slope, and the position of this line. So wherever these points lie, we can somehow find these parameters such that this line is fitted very well within these points, okay? And then when we have this specific line, then we can plug any value of x here, and this will output some prediction anytime, okay? So I'm going to slip and skip giving you a lot of details about how we can actually learn these parameters. But for this specific problem, it is quite straightforward and simple. But for larger models and more complicated models, it's a bit more, it's not complicated and difficult, but it is not a matter of a discussion in 1 hour for machine learning. So it is typically called gradient descent and back propagation. So if you want, we can discuss it in more details afterwards. But the idea is that you have data, input data, output data. N is the number of data you have. I is the number of dimensions you have in each of your columns. Then you have a predictor, which is your model, which is this function, which, again, I showed here the example of one-dimensional input, but you can actually have multiple dimensions as the input for the linear models. And then, in essence, all these different theta parameters is somehow a weighting a scheme, how you can actually sum all these values to make a prediction. And then the task is that the learning aspect of it is hidden here. And the idea is that you want to define some kind of metric or some kind of loss, as it is called, that at every time captures how close your prediction is to your true value, to what you want to predict. And this, in this specific case, you have the real target that you are interested in, which is this y, minus the output of your model, which is this one. Okay? So if you calculate this difference, you see how far or how you close the prediction is from the true value you want to do, to predict. And then if you add all these differences squared for all the data points you have here, then you have some estimate of how good or bad your model is doing. And you can use this information to update your parameters. Okay? And this is an optimization problem, which in this very simple case, it can be solved in 3 ways. One is, it is called the gradient descent. The other is called the stochastic gradient descent. And if a simpler one for this specific model is that there is actually a closed form solution to solve it. Okay? Which means that we know the solution for this. Okay. Questions? Okay. Yes. Yeah, you're right. I completely forgot to mention this. In fact, what you do is that you start from an arbitrary model. You just define your parameters in a random way. Typically, you actually do random, okay? You just initialize your parameters with random. You make a prediction for all your data points using this function here. After you made this prediction, you compare this prediction with your true value, what you want to predict, and then you have an estimate of how close or how far you are from the true function that you want to estimate. And then you can use this optimization problem, which tells you that I want to find which parameters theta are going to minimize this loss function for me. And this is an iterative process typically, or in the case of the linear model, the linear regression, it is actually a closed form and you can actually calculate it. Okay. Of course, this is a work that has been done years and years back. So there are publicly available tools that you can actually use that have all of this kind of functionality implemented. And you can find this here. We'll be using this in the following part, the workshop. So you'll have the chance to actually train a linear model yourself. And you will see that it's not like rocket science. Okay, just a twist on the linear regression. I'm just going to briefly talk about logistic regression. And the idea here is that before we were talking about predicting a continuous value. And now the difference with logistic regression is that instead of learning some continuous value, so now we cannot make direct comparison in terms of values of the prediction, we want our classifier to be trained such that it predicts in a classification scheme, okay? For example, a binary classification, which when your model needs to take either the value 0 or the value 1, okay? Which means that the input belongs to category 0 or belongs to category 1, okay? And for this, it doesn't make sense, our model, to get values larger than 1, for example. It only makes sense if you get 1 or not. And in fact, we want to make a very subtle and minor modification to our model and turn the output, remember this is the model, right? Input times the parameters. We want to make a minor modification to translate this output into some kind of probability. Are you aware of some way to do this? Okay, I'm going to say. So there is a function that is typically called logistic function. That's why also the term logistic regression, or a sigmoid function in some cases, where in fact takes the output of our model, which is this one, and this is this function, and transforms it such that it lies between the range 0 and 1 for all values, okay? So whatever our linear model will output, it will take this output and squeeze it in this range, 0 and 1, okay? Yes. This is, you can consider this as normalization, but in essence, you use this in order to compress your output of your model such that it lies at the range that you are interested in. And in fact, there is an extra step that you need to take. And now instead of learning the distance between the prediction and the target, you want to use some different probabilistic measure, which is called the likelihood, and it is defined as such, and tells you, so just quickly and very intuitively, the output of this loss function will be high when the model predicts with high confidence that this is one or the other. And it will be low when it is not confident for the right output, okay? So in essence, we change the linear model into a probabilistic model by enforcing that the output lies in the probabilistic range, and also by properly defining a specific loss function or a specific criterion that when it is maximized in this case, we are sure that our model is confident to predict the right answer every time. Okay. Is this a bit more clear now? Okay. Just a side comment on all these things that we are talking about is that we start simple. We try to understand the problem. We try to define our models such that it follows our understanding of the problem, follows some kind of aspects, like in this one, we want our range to be clipped, so we use this specific function. And then we make it learn using appropriate functions. And that's why these kinds of model can be quite how to say specific. You can design them as you want, okay, using the characteristics that you're interested in. Yeah, of course, this is already available, so you don't need to code it. Um, okay, moving on to the last parts of my presentation. So I just presented two models now, very, very simple models. One is the linear model, and the other is the logistic model. But there is many, many, many different models that again have this characteristic that they have some kind of trainable aspect of it. They are parametric, and you can learn their parameters such that to do what you want, more or less, by properly defining a loss function, which compares the output and to what you want as an output. And here I'm just showing you some examples. You have kernel-based models which enforce some kind of non-linear transformations to your input by design. Then you have models that are based on nearest neighbors. So the idea is that to find what is the class or the label for its most close example. Then you have decision trees that are kind of trees or branches that tells you check at every single node different characteristics, saying does this animal have pointy ears, yes or not, and then you follow a different branch. Then you have forests of randomly initialized trees, which are typically called random forests, and they're a quite stable baseline typically to use. Or again, neural networks, which is a hierarchical way to handle this data. We'll be talking about this. Also, Maria will talk about this tomorrow. And yeah, so these are all different kinds of models that you can use. But all the rest stays the same, right? You still need to have your data. You still need to have a loss function to compare how the prediction is comparing against the true value. You need to have the training scheme. You need to have the evaluation criteria, etc. So coming back again to the little discussion we had earlier, is that it is quite easy to build models to solve a specific task. You can define your most complicated model, have all the data in the world you can get, and you can find a way to make it such that your model performs very well on the data that you use for training. But the real question is how well this model can perform in unseen data. Actually, performing well also on unseen data, okay? On data that were not used for training. And we want to have this because we want our machine learning models to be useful somehow, okay? Even though, a side note here, these models can be useful only to understand the structure, but sometimes we want to use them in real time and real use cases, like making a prediction on prognosis, diagnosis, taking decisions about traveling directions and stuff. So we want to have models that generalize well, which means that we want to have models that can be used out of the training data. And we want also to evaluate our models and evaluate whether they are actually generalizing well. And there are different problems that we can encounter in these kinds of cases. Some of them is that we can have a lot of noise. And most of the times we actually have a lot of noise, which means that we can have imprecisions in measuring equipment. We can have errors in labeling because people are labeling things and people are not machines. So you can also have problems there. You can actually have a very important problem which is not easily identifiable, which is actually having biases in your labeling. So when we're talking about some kind of events or some types of language conceptions and stuff, annotators can have biases, okay? And if we have biases in our labels, our models are also biased. So the distribution of our data and the way our data is labeled is actually very, very crucial. And lately, guidelines, when you're releasing machine learning models and tools, require that you actually communicate all this information about labeling, handling, gathering data, etc. Okay, so if you get data from the internet, you will get what the internet knows. If you get data from experts, you will get what experts know, for example. And of course, we can have missing characteristics, missing features, which is very, very prominent in medical data, where not every annotator annotates everything. So you can have a lot of missing data, and there is a clear problem on how you can handle all this information. If your model is based on making a prediction on this missing data, what are you doing? Okay. There is the notion of overfitting and underfitting, which is actually talks about the fact that you can actually have models which are very, very precise and can very well fit your data. So here, this figure might be a bit weird to read, but you need to compare between these two models, the model which is in black line and the model which is a bit more smooth in the purple line. And the question is, which of these two models is the best? So in your training set, in your training data, maybe the black one is more accurate because you have all these blue dots are properly highlighted. But if you add new data, maybe this black model will not be so accurate. Okay. Here is again a similar example in terms of regression, where you have your model overfitting on your data, and you can have also the opposite effect, where your model is underfitting on your data. And the most kind of appropriate model is somewhere in the middle. Okay, and there is where people and engineers and data scientists and AI experts are spending a lot of time. I will finalize with different evaluation schemes that are typically used, and I will try to be quick. So as I mentioned, we have this training process, but we want to have some kind of data to use for validation purposes, to make sure that our model is performing well. Okay. Can you see any problem with this approach? Yes. So there are a lot of problems in actually defining and selecting what is this validation. So another problem that is a bit more practical is that if you want to select a number of models, you want to train a linear model, you want to train a decision tree, you want to train blah, 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 you want to train all these models, and then you want to see how all these models perform, you will actually going to check them in the validation set again and again and again. So there in this process comes a bias. And for this, we are not sure about what is the generalization error, because we never used unseen data to really evaluate. Among how we select the unseen data is also what is the scheme of training and evaluating every single model. A different way to approach this is to split them even more. So we have a training data, which is used for training a single model. We have a validation set, which is used to make sure that what we trained is doing well. We select using all these two, only these two sets, our best model, and then we apply it to see how generalizable is our model. And of course, a lot of problems comes again, because if the data set is small, if we keep splitting it again and again, the dimensionality and the number of samples at the different sets are going to be small again. So we'll be biased because of this. There are other ways to approach this. One is called cross-validation, and the other is called bootstrap. The cross-validation means that we select different validation sets from our training set, so we make sure that we have all the variability that is in our data set in a validation fold, as it is called. And there is leave one out, where you just leave a single sample out, you calculate everything, then you leave another sample out, and again and again and again. There are many different evaluation protocols. But in general, you have an original data set, which is the one you start with. A doctor comes and tells you, I want you to solve me the problem of subtyping of a specific cancer type, and I will give you 1,000 cases for that. Do whatever you want. So what you have to do is that you select a training set and then a test set where you keep it aside forever until the last evaluation point. Then you split your training set in two or multiple ones, multiple splits, and then you train algorithms, you evaluate their performance again and again and again. You select the final model, you test it, and then you present these results on your fancy publication eventually. Okay. There are a lot of information you can find here. Yes. Of course, you can definitely use whatever you have. The more you have, the better it is. This is something that we like to say to doctors. It never works. There is a threshold that data are generated. But yes, you can consider different schemes. So this test set can come from a completely different institute. And then you'll have to check how your model is generalizable for other data that are coming even from different acquisition protocols or things like that. And there is a lot of research on actually finding ways to minimize this generalization error across institutes. And one way is to use synthetic data for this. But yes, there are a lot of problems coming with this synthetic data. For example, you can generate synthetic text from ChatGPT, but maybe ChatGPT is biased because of the way it is trained. So this synthetic data, yeah, you know. Yeah. There are a lot of information here on how you can use all these evaluation protocols, yes. So a good test set is a test set that captures and holds data that captures all the variability that you can encounter, okay? So if you want to build a system that detects malignant versus benign cancers, for example, from very large images like histopathological tissue slides, you might want to have a lot of data here that capture all the different cases or the different patients that are diagnosed to have benign or malignant. And this is sometimes very difficult. Test sets need to have like appropriate sizes, needs to be have the minimal biases possible. It is actually very difficult on how to define this test set in order to make sure that your model is performing well. Okay, and that's why you need also to document what is all this evaluation protocol you used in order to train your model. If you are releasing something like that, if you're releasing ChatGPT, you need to know what it is trained on. Okay, from my point of view, because I don't have a lot of experience in maybe language models and other things like that. From the point of view of people working with clinical experts for clinical tasks, it's scientists like us, which understand exactly all these kind of problems, and also clinicians on the other side who understand the problem that we are trying to solve. So it's a very high interdisciplinary work that needs to be done, and this is happening through continuous meetings again and again with experts. I'm quickly wrapping up. You can find everything here. Last slides about performance metrics, things that you will probably see around. Typically, in order to evaluate these models, you use confusion matrices that look like this. They show you what is the true label and what is the predicted label, and you have something like that that tells you that 78% of the data were healthy and were predicted as healthy, but some 9% of them were predicted as this thing This is a slide coming straight from my PhD thesis. And there are a few others which I'm not going to go a lot of details. They are capturing different types of errors, like false positives, true positives, false negatives, etc. You can find everything here. Some of the reading material you can go through. Yeah. But these are very, very nice material to study. And that's all. Thank you.